In today's lecture, we're going to explore power series, and you're finally going to get to put to work all of the series tests that we've learned before. But first, let's do a quick review of geometric series. In our first series here, we want to begin by putting it in sigma notation. To move from the first term to the second term, we multiply by 1/2. And to move from the second term to the third term, we again multiply by 1/2. This is a geometric series where our absolute value of r is equal to the absolute value of 1/2. We can write this in sigma notation. N equal to 0. We see that our first term is 1, our second term is 1/2. When n is equal to 2, 1/2 squared is 1/4, and so the pattern holds for us. To determine if it converges, we need to know if our absolute value of r is less than 1. In this case, it is, so our series converges by the geometric series test, and we know that it is going to converge to a over 1 minus r. In this case, our a is 1, putting 1 in our numerator and dividing through by 1 minus 1/2 gives us 1 over 1/2, which is equal to 2. And so the infinite series from n equals 0 to infinity of 1/2 to the n converges to 2. In the second series, to move from the first term to the second term, we need to multiply 5 by -2 and divide by 3. Check from the second term to the third term to make sure that the pattern holds. Multiplying -10 thirds by -2 thirds gives us a positive 20 thirds. The pattern holds, telling us that the absolute value of r is equal to the absolute value of -2 thirds. Putting this in sigma notation, intuitively, we think that we should be able to begin like we did the previous series. Let's try -2 thirds to the nth power. But we want our first term, when n equals 0, to be 5, not 1. And so we need to multiply through by 5, which is our a value, our first term. We know that this is going to converge because our absolute value of r is less than 1, again converging by the geometric series test, and it will converge to a, which is 5, over 1 minus -2 thirds. Simplifying in the denominator, we have 5 over 1 plus 2 thirds, that is equal to 3 thirds plus 2 thirds, giving us a 5 thirds in the denominator. The 5s are going to cancel out, and 1 over 1 third is equal to 3. So this series will converge to 3. In the last series, we've never seen one like this, where we have x's instead of numbers. But the same pattern as the two above still holds. To move from the first term to the second term, we need to multiply by x. Then to move from the second term to the third term, we again multiply by x. This is a geometric series with a equal to 1 and r equal to x. Just like in our previous two examples, this geometric series is going to converge when the absolute value of r, which in this case is equal to the absolute value of x, is less than 1. So as long as x is between -1 and +1, we can express this as a over 1 minus r. In summation notation, we have the sum from n equals 0 to infinity of x to the n, and that is equal to 1 over 1 minus r, and here our r is x. Even though this doesn't look like one of our geometric series above, it still has that same general form. Whenever we have a series that is in terms of x and fits in a certain standard form, then we call that a power series. But what exactly is that certain form that it needs to be in? A power series centered at x equal to a has the form of the sum from n equals 0 to infinity of c sub n times x minus a raised to the nth power. The c sub n is our coefficient, c for coefficient. A is where our power series is centered. And when you start expanding the terms of the power series, it becomes an infinite polynomial. Think of this as a polynomial on steroids. Why are power series so important then? From the previous slide, we were able to express the function f of x equal to 1 over 1 minus x as a polynomial, as long as our absolute value of x is less than 1. And there's a lot of things that we can do with a polynomial that are significantly easier, such as taking the derivative and integrating, just to name a few. One quick side note before we move on. This power series is in what we call standard form. Unlike with geometric series, where I said you could ignore the standard form altogether, for power series, you need to be familiar with standard form. It becomes important later. We can't always express every function as a power series, and even those that we can, many of them, we cannot express them as a power series for all values of x. For example, when x is equal to 2, subbing in to the power series from the previous slide, on the left-hand side of our equation, 1 over 1 minus 2 simplifies to negative 1. Subbing in x equal to 2 on the right-hand side gives us 2 to the n. Writing this out longhand, when n is 0, we have 1, plus when n is 1, we have 2, plus 4, plus 8, and we would go on forever. Clearly, the right-hand side of this equation is not equal to the left-hand side. So when can we express a function as a power series? F of x can only be expressed as a power series of that form, our standard form, the sum from n equals 0 to infinity of c sub n times x minus a to the n if the series converges. In the case of a geometric series like above, this is easy. We know they converge when the absolute value of r is less than 1. But we want to be able to express more than just geometric series as functions. The interval of convergence, which we can abbreviate as IOC for short, for a power series in standard form is the set of x values for which that power series converges. Occasionally, the geometric series test is useful, but most of the time, you're going to want to use the ratio test. In our first example, we want to find the interval of convergence for the power series, the sum from n equals 0 to infinity of x minus 3 to the n over 2 to the n times the square root of n plus 1. Big picture here. We're looking for all of the x values for which this series converges. And we know from the ratio test that a series a sub n is going to converge when the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. Let's start by naming our test, the ratio test. The limit as n approaches infinity of the absolute value of a sub n plus 1 Plugging in n plus 1 everywhere we see an n into our series, we have x minus 3 raised to the n plus 1 over 2 to the n plus 1 times the square root of n plus 1 plus 1. Instead of dividing by a sub n, we'll multiply by the reciprocal of a sub n. In the numerator, we have 2 to the n times the square root of n plus 1 over x minus 3 to the n. Unlike in last lecture, where we could drop the absolute value signs as soon as we dropped the alternating part of the series, here we need to keep the absolute value signs the entire time because x could be positive or negative. This is equal to the limit as n approaches infinity times the absolute value of x minus 3 raised to the n plus 1 over x minus 3 to the n times 2 to the n over 2 to the n plus 1 times the square root of n plus 1 over the square root of n plus 1, which is n plus 2. Whenever you're using the ratio test, grouping your like terms like this is always going to be easier. And I like to put the polynomials last. That's because if we look at this limit as n is going to infinity, it's indeterminate. We have something growing without bound in the numerator and something growing without bound in the denominator. And so in order to evaluate this limit, we need to multiply through by 1 over the highest powered term in the denominator, which is 1 over the square root of n. I'm going to get rid of our absolute value sign, 1 over the square root of n over 1 over the square root of n. And now I'll add the absolute value sign back in. Simplifying our limit, we have the limit as n approaches infinity of the absolute value of x minus 3 times 1/2. 2 to the n divided by 2 to the n plus 1 is 1 over 2. Distributing the 1 over the square root of n through the square root of n plus 1 gives us the square root of 1 plus 1 over n over the square root of 1 plus 2 over n. And closing our absolute value signs, we now have a limit that we can evaluate. This is equal to the absolute value of x minus 3 divided by 2. And as n is going to infinity, in the numerator of the last term, this becomes the square root of 1 plus 0. And in the denominator, we have the square root of 1 plus 0 as well. That simplifies down to the absolute value of x minus 3 over 2. The ratio test tells us that the series will converge when the absolute value of x minus 3 over 2 is less than 1. Solving for x, let's multiply both sides through by 2. The absolute value of x minus 3 is less than 2. To drop the absolute value signs, we can rewrite this as negative 2 less than x minus 3 less than 2. Adding 3 to both sides, we have 1 less than x less than 5. That tells us that our series, the sum from n equals 0 to infinity, of x minus 3 raised to the n over 2 to the n times the square root of n plus 1 converges when x is between 1 and 5. But think back to the ratio test. When the limit as n approaches infinity of a sub n plus 1 over a sub n the absolute value of those terms, is equal to 1, the ratio test is inconclusive. In other words, when x is equal to 1 and when x is equal to 5, this limit is going to equal 1. And so to determine if the series converges or diverges at the endpoints 1 and 5, we have to use other tests. Since we want to know if the series converges when x is equal to 1 and 5, we're going to sub in x equal to 1, and then we'll sub in x equal to 5 to see if the series converges at each of those endpoints. Let's start at x equal to 1. Always label which endpoint you're testing. It's so important it gets 2 exclamation marks. We have the sum from n equals 0 to infinity. In place of x, we sub in 1, minus 3 to the n over 2 to the n times the square root of n plus 1. Simplifying that, we have the sum from n equals 0 to infinity. In the numerator, we have negative 2 to the n divided by 2 to the n times the square root of n plus 1. We can use our exponential rules to simplify this. We know that if we have a times b raised to the nth power, we can rewrite that as a to the n times b to the n. Let's use that to rewrite the negative 2 to the n in the numerator. The sum from n equals 0 to infinity. In the numerator, breaking that up, we have negative 1 to the n times 2 to the n over 2 to the n times the square root of n plus 1. The 2 to the n in the numerator cancels with the 2 to the n in the denominator, leaving us with the sum from n equals 0 to infinity of negative 1 to the n over the square root of n plus 1. This is an alternating series, so to determine if the series converges when x is equal to 1, let's use the alternating series test. The limit as n approaches infinity of b sub n, here we have 1 over the square root of n plus 1, is equal to 0. This is clearly true. We need our terms to be positive and decreasing. 0 is less than or equal to 1 over the square root of n plus 1, plus 1 less than or equal to 1 over the square root of n plus 1. Because we have a 1 in the numerator and something that is clearly larger in the denominator, we can say that this inequality is clearly true. For all n greater than or equal to 0. This tells us that the sum from n equals 0 to infinity of negative 1 to the n over the square root of n plus 1 converges by the alternating series test. That means that our original series, the sum from n equals 0 to infinity of x minus 3 to the nth power over 2 to the n times the square root of n plus 1 converges when x is equal to 1. Let's check our other endpoint. At x equal to 5, remembering to label here as well, we have the sum from n equals 0 to infinity. Subbing 5 in for x, we have 5 minus 3 raised to the n over 2 to the n times the square root of n plus 1. In the numerator, the 5 minus 3 to the n, that's equal to 2 to the n, which cancels out with the 2 to the n in the denominator, giving us the sum from n equals 0 to infinity of 1 over the square root of n plus 1. This isn't geometric, it's not a p-series. We need to use the comparison test. Let's do a little scratch work to find our compare to series. 1 over the square root of n plus 1 is going to be similar to 1 over the square root of n for very large n. And we know that the sum from n equals 1 to infinity of 1 over n to the 1/2 diverges by the p-series test, p equal to 1/2, which is less than 1. That tells us the direction that we want our inequality to go. Since we think that our series is going to diverge, we want to prove that 1 over the square root of n plus 1 is going to be greater than or equal to 1 over the square root of n. But we can see right away that this inequality is not true. We need to make 1 over the square root of n smaller. So instead of putting that 1 in the numerator, for now, just as a placeholder, we'll say c. We can use our finesse method to find the value of c, which makes this inequality true. For the first part of the comparison test, proving the inequality, we have 1 over the square root of n plus 1 greater than or equal to 1 over the square root of n plus 1 times n. Since n plus 1 is going to be less than or equal to n plus n, for all positive integer values of n, we know the reciprocals, 1 over the square root of n plus 1, will be greater than or equal to 1 over the square root of n plus n. This is greater than or equal to 1 over the square root of n plus n is the square root of 2n. And we can simplify that by bringing the 1 over square root of 2 up into the numerator and leaving the square root of n, or n to the 1/2, in the denominator. And this is going to be greater than or equal to 0 for all n greater than or equal to 1. Notice it's not true when n is equal to 0, and so we're going to have to deal with that first term when n equals 0 separately. We'll do that in our conclusion. For the second part of the comparison test, we need to prove that our compare to series, the sum from n equals 1 to infinity of 1 over the square root of 2 over n to the 1/2, diverges, which it does because it is a p-series, where p is equal to 1/2, which is less than 1. We've proven both parts of the comparison test. Let's give our conclusion. Since 1 over the square root of n plus 1 is greater than or equal to 1 over the square root of 2 over n to the 1/2, which is greater than or equal to 0 for all n greater than or equal to 1, and the sum from n equals 1 to infinity of 1 over the square root of 2 over n to the 1/2 diverges, then 1 plus the sum from n equals 1 to infinity of 1 over the square root of n plus 1 is equal to, and this 1 in front, that is the first term of our series when n is equal to 0. Letting us rewrite this as the sum from n equals 0 to infinity of 1 over the square root of n plus 1 diverges by the comparison test. Now that we know whether our original series converges at the endpoints, we can finally give our conclusion. The interval of convergence for the sum from n equals 0 to infinity, x minus 3 to the n over 2 to the n times the square root of n plus 1 is from 1 to 5. Since the series converges at 1, we want to use a bracket. It includes the endpoint 1. And since our series diverges at x equal to 5, we want to use a parentheses there. I know many of you prefer the less than or equal to and the less than notation, but I wanted to teach it this way because you'll need to know this notation for your web work problems. Let's summarize what we just found. We've shown that our power series converges when 1 is less than or equal to x less than 5. Notice that the center of that interval between 1 and 5 is x equal to 3. And our power series in standard form is also centered at x equal to 3. This is always true. This is a very easy check you can do when you've finished taking the limit in the original ratio test and finding the values for which your limit is going to be less than 1. If the center of those values is not the same as wherever your series is centered, you know you've made an algebra mistake. Since our series is centered at 3 and our endpoints are at 1 and 5, the endpoints are a distance of 2 from the center, and we call this the radius of convergence. And we notate it with just a capital R. So in this case, for our series, we have that R is equal to 2. Read the wording on the questions carefully because sometimes you'll be asked to find the interval of convergence, which means you do have to check your endpoints, and sometimes you'll be asked only for the radius of convergence, in which case you don't have to check your endpoints. Let's do another example. In the next example, we want to find the interval of convergence for the power series -1 to the n times x to the 2n over 2n factorial. Notice that our power series is not in standard form, but it's still a power series because we can rewrite x to the 2n as x squared raised to the n. Even though we don't have it in the form of x minus a raised to the nth, we can still determine where this is centered because instead of x, really what that is x minus 0 raised to the 2n. And so this power series is centered at x equal to 0, which means that whatever interval of convergence we find, it has to be centered at x equal to 0. We'll begin with the ratio test. The limit as n approaches infinity of the absolute value of, in the first term, everywhere we see an n, we want to replace it with n plus 1, giving us our a sub n plus 1. So we have -1 to the n plus 1 times x to the 2 times n plus 1 over 2 times n plus 1 factorial. This is times the reciprocal of a sub n, which is 2n factorial over -1 to the n times x to the 2n. This is equal to the limit as n approaches infinity of the absolute value. And grouping our like terms, let's start with our x terms. In the numerator, distributing the 2 over the n plus 1, we have x to the 2n plus 2, and that's divided by x to the 2n. We can close the absolute value signs, only contain the x terms, because we know that n is starting at 0, and from there, it's always going to be a positive integer. That means that the factorial terms will always be positive, and the absolute value of -1 is just 1. Bringing down our factorial terms, in the numerator, we have 2n factorial, and we know from Monday's lecture that 2n plus 2 factorial is equal to 2n factorial times 2n plus 1 times 2n plus 2. Subbing that in our denominator, we have 2n factorial times 2n plus 1 times 2n plus 2. To simplify this, we can use our exponential rule that x to the a over x to the b is equal to x to the a minus b, giving us the limit as n approaches infinity of the absolute value of x squared times 1 over 2n plus 1 times 2n plus 2 is equal to 0. And 0 is less than 1 for all values of x. And so our series converges for all values of x. That tells us that our interval of convergence is from -infinity to positive infinity. We weren't asked to find the radius of convergence, but if we were, then we would write r is equal to infinity. And just a quick note on notation. Whenever one of your endpoints is either -infinity or positive infinity, you want to always use open parentheses, never the brackets. Let's do one more example. We want to find the radius and the interval of convergence for the power series n factorial times x to the n over 5 to the n. We start the same way as before, using the ratio test. The limit as n approaches infinity of the absolute value of n plus 1 factorial times x to the n plus 1 over 5 to the n plus 1 times the reciprocal of a sub n gives us 5 to the n over n factorial times x to the n. Simplifying, this is equal to the limit as n approaches infinity. Let's group our like terms. We have the absolute value of x to the n plus 1 over x to the n times 5 to the n over 5 to the n plus 1 times, in the numerator, we can rewrite n plus 1 factorial as n factorial times n plus 1. And in the denominator, we have n factorial. This is equal to the limit as n approaches infinity of the absolute value of x times 1/5 times n plus 1, where both our n factorial in the numerator and the denominator cancel out. And we want this limit to be less than 1. But as n is approaching infinity, the n plus 1 is growing without bound. And so this entire limit is diverging to positive infinity, except when x is equal to 0, we have the limit as n approaches infinity of 0 times n plus 1 over 5 by our order of operations. And this is equal to the limit as n approaches infinity of 0, which is equal to 0. And 0 is definitely less than 1. That means that our radius of convergence is 0, and our interval of convergence is a single point. To represent a point in interval notation, instead of using parentheses or brackets, we use the squiggly brackets. I seem to recall that might also be helpful in one of your web work problems. Let's recap what we've done so far. The interval of convergence is always symmetric, except at the endpoints, about the center. So let's say that we're given a power series, c sub n times 3 to the n converges, but that same power series, c sub n times negative 5 to the n, diverges. What can we say about each of the following series? Think back to our standard form of power series. It has to be in this form of some constant times x minus a to the n. And for this example, it's going to be easiest if we center our series at x equal to 0. That means we know that the standard form for our power series is now going to be some constant times x minus 0 to the n, which simplifies down to c sub n times x to the n. That means that when we're given the sum from n equals 0 to infinity of c sub n times 3 to the n converges, what that is telling us is that when x is equal to 3, the series converges, just subbing in for 3 in place of x. We're also given the sum from n equals 0 to infinity of c sub n times negative 5 to the n diverges. And what that means is that when x is equal to negative 5, the series diverges. Let's put that on our number line.
Our series is centered at x equal to 0. So let's start by marking that on our number line. We know that the series converges when x is equal to 3. Think back to your interval notation. When it converges at an endpoint, we use the close bracket. We'll follow the same notation here too. So I'll put a closed bracket at x equal to 3. We know then that our radius of convergence is going to be at least 3. And by symmetry, the series will have to converge between negative 3 and 0 as well. But symmetry doesn't hold at the endpoints. Just because our series converges at x equal to 3 doesn't necessarily mean that it has to converge at x equal to negative 3. That means instead of a closed bracket at negative 3, we have to put an open parentheses. We're also given that our series diverges when x is equal to negative 5. That means on our number line, let's put a closed bracket at x equal to negative 5, and our series is going to diverge for all values of x less than or equal to -5. By symmetry, then, that means whenever x is greater than 5, the series also has to diverge. Because symmetry doesn't always hold at the endpoints, though, we don't know whether our series converges or diverges at 5, which means we'll put an open parentheses at 5. We know that whenever our x value falls between -3 and 3, our series will converge. And whenever the x value is greater than 5 or less than or equal to -5, our series will diverge. So now we have enough information to answer this question. In the first series, we only have c sub n. It doesn't look like there's an x value there, but really, this c sub n is multiplied by 1. Going over to our number line, when x is equal to 1, we fall within our radius of convergence, and so we know that our series converges at x equal to 1. Going back to our series, we can say converges. For the next series, we have c sub n times 6 to the n. That means that our x value is 6. Going over to our number line, we can see that when x is equal to 6, we're in the interval where the series has to diverge. That means that our series, c sub n times 6 to the n, diverges. For the last series, we have that x is equal to -4. Looking at our number line, when x is equal to -4, we're neither within the interval of convergence, nor are we in the intervals where we know the series has to diverge. That means that at -4, we don't really know what the series is going to do. It could converge or diverge. In this case, there's just not enough information to go off of. You'll see similar problems to these in workshop tomorrow and also in your homework. So when you do, this is how you would show your supporting work for these types of problems. Use a number line to show the intervals where you know your series converges and diverges, and where your x values fall in relation to those intervals. In today's lecture, we could express the function 1 over 1 minus x as a power series, but mostly we focused on when power series converge and how do you determine this. Next week in lecture, we'll learn how to express other common functions besides 1 over 1 minus x as power series.